Okay, this is a solution to linkages number 9. This is a pretty complicated problem. Goes on and on. Well, let's get started. So here's the geometry of the problem. So we have a member there and a member there. These are at a right angle. And from the lengths that are given, we know that the length of the left piece is 1.2. The length of each half of the right piece is 0.9. And since it's a right triangle, that means that this is a 3, 4, 5 right triangle. And this length is 1.5. That's right, isn't it? Yeah. And then we have the disk. And so that's a connection point to the disk, but that point is not connected to the ground. And then the center of the disk is connected to the ground. So the disk rotates about the center, and as it rotates, it cranks this arm and turns this 4-bar linkage, and we're trying to figure out something about this point A up here. What do we know? So let's name these members. Let's call this member 1, this one member 2, this one member 3, and let's name the joints. I'll call this A, B. Oh, we already have an A, sorry. So let's call this one down here B. I'm going to call this C, D, and E. I don't know. That's what I'm going to do anyways. So what do we know? We know that at the instant shown, body 3 has an angular velocity of -5, and that's in the z direction, so 0, 0, -5. What about the other two things? We're not given those. Well, it turns out that in order for this thing to stay connected at the pins at E and D and C, B, E, D, C, all those pins, there's only one combination of angular velocities that's possible for body 1 and body 2, and we're going to have to calculate what that is. Okay. Well, let's see. We could do that at the end once we get to the constraints. I think that's probably a good way to do it. We'll just start out with this like a normal linkage problem, and then we'll go back and do the constraints later. Okay, so I'm going to start out with a free body diagram of member 1. And from the geometry, let's see, what do we know about this? Well, we know that the arctangent of 3/4 is the angle that this member makes with the horizontal. So the arctangent of 3/4 is 36.87 degrees, so that's this angle. And we know there's a force vector here. I'll call that R. What did I call that joint? RB. And there's a mass. So there's a weight of 10 kilograms times 9.81, so 98.1. And then there's a force here at the pin. That's the force on member 1 by member 2. And I'm sort of doing this stuff out of order. So for a rigid body problem, I always say, start by figuring out if there's a fixed point. There is a fixed point, and that means we have to calculate the moment of inertia about the fixed point. So the moment of inertia, we're going to do it about that pin B, and that's equal to 1/12 times the mass times the length of this member squared, so 1.2 squared, plus, now we have to use the parallel axis theorem, the mass of 10 times the distance from the center of mass to the point B. That's half of the length, so that's 0.6 squared. And for that, you get 1.2 squared times 10 divided by 12. Why am I mumbling? So you get a moment of inertia about that pin B of 4.8. And the units are kilogram meters squared. Okay, and the about point is B. I already did the free body diagram, so now I can write out this table of rho, force, and moment. Okay, well, let's start with RB. That's at the about point. So the rho vector is 0. The force vector is RBX, RBY. Let's just do this in 2D. And so there's no Z component of the moment. Then is the weight force. So the rho vector for that is 0.6 times cosine and sine of that angle, 36.87. So that's 0.480. And 0.360. And the force vector is 0, negative 98.1. So that's 47.09 negative. And the last one is that force F12. The rho vector there is just double this one, so that's 0.960, 0.720. The force vector is F12x, F12y, and the cross product is 0.96 F12y minus 0.72 F12x. Okay, and then Newton's second, okay, so now we have to think about, do we need Newton's second law? And we have a fixed point, so we don't need it yet. Maybe later we could use it to calculate a reaction force at B if we wanted. You know, that's really the only reason you would ever use it. So for now, we're going to say we don't want it. So no Newton's second law. And now we'll go to the moment equation about the z-axis. And it says, so I'll write it as negative 0.72 F12x plus 0.96 F12y minus 47.09 is equal to the mass moment of inertia, 4.8, times alpha for body 1. Okay. And I'm going to rewrite this equation as negative 0.72 F12x plus 0.96 F12y minus 4.8 alpha 1 is equal to 47.09. And I'll call that my equation star. That's my first useful equation. How many variables do we have? Well, we have some, like notice RBX and RBY. We have them in our table, but they don't show up in our equations. So for now, we have one equation, and we have 1, 2, 3 variables. That's F12x, F12y, and alpha 1. And now we'll go on to body 2. And so I'm going to do this one in the right order. Okay, does body 2 have a fixed point? No, every point on body 2 can move relative to the coordinate system. And so the mass moment of inertia of body 2, we're going to use about the center of mass. That's 1/12 times the mass of that body, which is 15, times the length of that body squared. .05. And now we can draw the free body diagram. This is body 2. Our center of mass is the about point. And the forces we have the force on 2 by 1, which is negative F12. We have the weight force, which is 15 times 9.81, 147.15. And then we have here the force on 2 by 3. And now we can write out the table. Two of these forces happen at the center of mass, so there's no row vector. So the negative F12 row vector is 0. The force vector is negative F12x, negative F12y, and the moment is 0. The weight force, also row vector of 0. The force is 0, negative 147.15. Moment is 0. And then the last one is that force F23. Okay, so what's that? Well, you can think of that, it's perpendicular to that last member. So you can think of it as the vector that's going from the center to that point at the bottom right is 30, the angle we had before, which is 36.87 minus 90. So that gives us our angle. And then it's times the length from there, which is 0.9. Okay, so the row vector is 0.54, negative 0.72, the force vector is F23x, F23y, and the cross product is 0.54 F23y plus 0.72 F23x. All right, do we need Newton's second law for this? Yes, because there's no fixed point. So Newton's second law says negative F12x, negative F12y, plus 0, negative 147.15, plus F23x, F23y, is equal to the mass of this body, 15, times the acceleration of the center of mass. I'm going to call that A2. And the moment equation says 0.72 F23x plus 0.54 F23y is equal to the mass moment of inertia that we calculated, 4.05. Times the angular acceleration of body 2. And so that gives us 3 more equations. We have one that says negative F12x plus F23x minus 15A2x is equal to 0. The second one says negative F12y plus F23y minus 15A2y is equal to 147.15. And then the third one says 0.72 F23x plus 0.54 F23y minus 4.05 alpha 2 is equal to 0. So this one's equation 2 star, 3 star, and 4 star. And what do we have for equations now? Well, we had for variables, sorry. We had 3 variables before, f1, 2, and alpha 1. So I'll just write it out as, so we got f1, 2, the vector, alpha 1. Now we have f2, 3, the vector a2, that's the center of mass of 2, and alpha 2. So we have 2, 4, 6, 7, 8 variables and 4 equations. And now we'll go to body 3. This one does have a fixed point. And the fixed point is the center of mass. So our I is about the center of mass. And that is 1/2 times the mass of 50 times the radius squared. So we have 50 over 8. .25 kilogram meters squared. And now we'll do a free body diagram. There's a force here. That's what I called C, so I'll call this reaction force RC. There's a force down here. That's the force on 3 by 2, or in other words, that's negative F23, because we already have an F23. And then there's one more thing. There's a couple of negative 150. I'm going to draw it in the positive direction and just write it as negative 150. You could also draw it the other way and call it positive 150. Okay, the geometry on this one's easy. That's the good news. So rho, force, moment. So first I'll do RC. The about point is the center, so the rho vector is 0. The force vector is RCX, RCY, and there's no moment. Oh, I didn't do the weight force, sorry. Okay, I'm going to draw it like this. 50 times 9.81, that's 490.5. So now the weight force also happens at the center of mass at the about point. That's 0, negative 490.5. The moment is 0. Then we'll do the 150. We don't care about these for couples, and that is negative 150. And then the last one is our negative F23. The rho vector, the radius is 0.5. So the rho vector is 0, negative 0.5. The force vector is negative F23x, negative F23y, and the moment is negative 0.5 F23x. This has a fixed point, so we don't have to do Newton's second law. The moment equation says negative 150 minus 0.5 F23x is equal to the mass moment of inertia times the angular acceleration for this body. And that gives us our fifth equation that says negative 0.5 F23x minus 6.25 alpha 3 is equal to 150. And we only got two new variables here. Although I think we're probably going to have to use that y. Well, let's just take into account what we have so far. So variables, we had 8 before. The new ones that we included, oh, well, we've already dealt with F23y before, so it doesn't matter either way. So we have F12, alpha 1, F23, A2, alpha 2, and that's our first 8, and then we also have alpha 3. So we have 9 variables for our 5 equations. And that means that we're going to need 4 constraint equations. Which is going to come in the form of 2 vector equations saying that accelerations agree for the 2 bodies at the joints. Okay, well, before we do that, we're going to have to figure out angular velocities. Okay, so these are acceleration constraint equations. But to come up with expressions for the accelerations, we're going to need to know the angular velocities of all these bodies. You know, to get expressions for those accelerations. And those constraint equations are going to work the same as the acceleration constraint equations. We're just going to say that the velocities at those joints have to match. Okay, so we want to find omega for 1 and omega for 2 by requiring the velocities to match at the joints. Okay, so first let's make the velocities match at, if we scroll up to the original picture, at D. So we're going to find the velocity on that wheel, and we're going to come up with an expression for that angular velocity of body 2 in terms of the angular velocity we're given for the wheel. Okay, so according to the wheel, the velocity at that point D is easy to calculate. That's just omega of body 3 crossed with the vector that goes from the center of the circular motion to D. So that's 0, 0, -5, that's given, crossed with 0, -0.50. And so the velocity at that point D is equal to -2.5 for x, 0, 0. This is meters per second. Now, we'll come up with an expression for the velocity of D according to body 2. And this one, we're going to have to use relative motion because there are no fixed points on that. So we're going to have to think of, so the velocity of D relative to the ground is equal to the velocity of D relative to the center of mass of 2 plus the velocity of the center of mass of 2 relative to the ground. And the center of mass of 2 is the joint, let's see what I called that. That is the joint E. Okay, so this is the velocity of E. Okay, so the velocity of D relative to the center of mass of 2 is 0, 0, omega 2 crossed with the R vector. And we already calculated that R vector a long time ago. It was a row vector before. That is the one, that is 0.54, -0.72. Okay, so that is, the x component is positive 0.72 omega 2. The y component is positive 0.54 omega 2, and then 0 for the z component. And so the velocity of D, which is what we're trying to get, is 0.72 omega 2, 0.54 omega 2, plus the velocity of E, X, and Y components. Okay, so our constraint equation at D says negative 2.5 0 is equal to 0.72 omega 2, 0.54 omega 2, plus VEX, VEY. I can write this as two equations. So we have 0.72 omega 2 plus VEX is equal to negative 2.5. And then 0.54 omega 2 plus VEY is equal to 0. Okay, so that's our first. So remember where we are. We're trying to calculate these omegas so we can go on to our usual constraint equations, which have to do with angular accelerations. So we have our constraint equations at D. We can't solve them yet. And now we want our constraint equations for velocity at E. And that's just going to say that this variable VE is equal to, so that's equal to the velocity that we calculate from the left member. Okay, so according to member 1, the velocity at E is equal to omega of 1 crossed with the r vector. So 0, 0, omega 1 crossed with, and we also have that r vector up above. That is 0.96, 0.72. And so that gives us negative 0.72 omega 1 and positive 0.96 omega 1, 0. And that's our VE. So now we can plug that in for the VE up here. Okay, so I'm going to take these two things. And what we have is 0.72 omega 2 minus 0.72 omega 1 is equal to negative 2.5. And 0.54 omega 2 plus 0.96 omega 1 is equal to 0. Okay, that's a simple system of equations to solve And you get that omega 1 is 1.25. And omega 2 is negative 2.22. And now that we have that, if you had a nice dynamics professor, they would have given you those values. And then you could just go on to the step we're at now, which is finding those acceleration constraints. Okay, so finally, we're on to the acceleration constraints. Okay, well, we have to say that the accelerations at these three joints, D, E, I guess just those two joints, match. So I'll start with joint D. And again, we're going to have to do it according to each member. So according to 3, the acceleration of D is equal to, we have to use the watermelon equation, so 0, 0, alpha 3 crossed with the R vector, 0, negative 0.5, 0, plus, now we know these omegas, omega 3 we were given, so 0, 0, negative 5 crossed with the quantity 0, 0, negative 5 crossed with that R vector. This one is negative 2.500. And so cross it with that, and you get 0, positive 12.5, 0. Cross this one, and you get positive 0.5, alpha 3, 0, 0. So according to member 3, the acceleration of that point D is 0.5 alpha 3. I'm just adding these together. 12.5. I'll leave off the Z component. None of these are going to have any motion in Z. This is all planar motion. And now according to member 2, we have to use relative motion again for this. So it's going to be the acceleration of D relative to the center of mass plus the acceleration of the center of mass. I'm just going to add on the acceleration of the center of mass at the end, but relative motion is why that's going on. So the acceleration of D is equal to 0, 0, alpha 2 crossed with the R vector, which we have up here above, 0.54, negative 0.72. Plus omega times omega cross r cross omega cross quantity omega cross r. Body 2 has a omega of negative 2.22. Crossed with 0, 0, negative 2.22, crossed with the r vector, for this whole thing, you get negative 2.66, 3.55, and for this one, you get, for the x component, 0.72 alpha 2. For the y component, you get 0.54 alpha 2. And so this comes out to be 0.72 alpha. I'm going to rewrite that somewhere else. Okay, so this is equal to 0.72 alpha 2 minus 2.66, 0.54 alpha 2 plus 3.55. And now you can set these two equal to each other. The ADs have to match. So we have 0.5 alpha 3 minus 0.72 alpha 2 is equal to negative 2.66. I just moved everything. So I set these two equal and just moved everything over to the left side. And then we have 0.54 alpha 2 is equal to 3.55 minus 12.5. So negative 8.95. We had how many equations? 5 equations. So this is equation 6 and 7. And now we're getting really close. The acceleration constraint equation at the joint E is going to be easy. Okay, so now we're at joint E. Well, joint E, according to member 2, that's just the center of mass, and we have a variable for that. So AE is just equal to the acceleration of the center of mass of 2. Yay. Okay, so according to member 1, the acceleration of E is equal to the angular acceleration of body 1. That's 1.25. Oh no, angular acceleration, sorry. I'm getting ahead of myself. So 0, 0, alpha 1, crossed with that r vector, which is this one, 0.96, 0.72. And that's equal to 0, 0, 1.25 crossed with 0, 0, 1.25 cross R. So this part comes out to be negative 1.5, negative 1.125. And this one comes out to be negative 0.72 alpha 1, positive 0.96 alpha 1. And so so these equations, well, let me write this out. So AE is equal to negative 0.72 alpha 1 minus 1.5, 0.96 alpha 1 minus 1.125. And so the constraint equations say A2x plus 0.72 alpha 1 is equal to negative 1.5, and A2y minus 0.96 alpha 1 is equal to negative 1.125. And those are equations 8 star and 9 star. Whew. And we have 9 variables, so 9 equations will solve it. So now I'm going to spend a little time solving this, but you don't have to see it because of the magic of time-lapse cinematography. And when you put all that together, you get an answer for the acceleration of A of 17.95 negative 2.20 meters per second squared. You can see from this, you wouldn't want to do very much more complicated machines than this by hand, but this approach is really, suitable to computer programming. So writing a program that would calculate stuff like this is not really any more effort than doing it by hand, and then you can do it for all the calculations you want. Whew. Okay, that one is nasty. That is number 9 in linkages.